Hello guys, hello everyone. Welcome to the P1 program. This lecture is called P107.5, right? So in this lecture we are going to look at this is the last part of the circular motion lecture. We are going to look at non-circular motion in this lecture. Okay, non-circular motion. So far we have discussed about the theta, changing theta with respect to time, and we have found out the acceleration, we have found out the velocity, we have found out the omega, which is angular velocity, and then there is alpha, which is angular acceleration. So we did that. Now we need to do is just uh, go away from circular paths, right? So if it's a perfect circle, then there is a restriction, right? The restriction is to always bound your path around this circle's perimeter, right? You cannot go away from that. So now we need to look at paths, right? Circular paths, non-circular paths, which are somewhat different from these circular paths, with the radius is constantly changing, right? So it could be anything, right? Radius is also a function of time. So I have actually mentioned that in some part of the lecture, but we haven't done anything based upon that. So this is a fresh start for a fresh topic, which is very useful for you guys to find out the trajectory and the different aspects of motion for particles who are moving around in not in circular paths, right? So far what we have learned, right, we have to use some of those factors, most important factors. So far we have learned that a vector r can be written as r of t times r cap, right? A basic representation of vector, right? This is the magnitude. And we have in the first lecture, which is of this section, which is 107.1, we have formulated some of the things, right? So initially first one was that r cap can be written as cos theta in time in the x cap direction, and we are going to use this in here. That's why I am mentioning things right again. Okay, so don't be confused, I'm not saying it again and again, but we need to use it right now. So this is the final part of this lecture where we are going to use these principles. So bear with me for a moment. So cos theta is equal to y cap. So this was what the positional coordinates were, right, in terms of r and theta cap direction. Now what we are going to do is that we have also found out, let's call this equation 1, right? So let this be equation 1. Okay, and we have also found out that dr by d theta, right, dr cap by d theta was equal to theta cap times d theta by dt. In the first lecture we did this, and similarly we also did d theta cap by dt, which is the time rate of change of unit vectors in dimensions. In those vectors transform into these two forms, right? In the r cap direction it transforms like this, and in theta cap direction the transformation of unit vectors minus times minus d theta by dt in the r cap direction, right? So these two were things that we have found out, right? Now before here, so let's call this equation 2 as well. Now before here, before this lecture, this is all the things that you have learned. You have also learned about the velocity vector, if you remember. So velocity vector was something like, which is has v of theta in the theta cap direction, which is equal to r times d theta by dt in the theta cap direction, right? So that was also something that we have derived. Now what I'm going to do is that I'm going to simply start from scratch for the non-circular motion. So as we have mentioned, the r is just r of t, right? R of t, vector r is just r of t in the r cap direction, right? So that's the magnitude. So velocity, right, now r has become a function of time, right? So r is now a function of time. Earlier it was a constant. Now what happens is when you calculate the velocity vector, which is dr by dt, right? So when you do that, what happens is that you have two functions which are equally as functions of time, right? So you have to apply the product rule, and you get the first function. You can do it dr first function, derivative of first function dr by dt, which is a function of time. I'm not going to write it always, times r cap plus this first function r times dr cap of by dt, right? So this equation, this is an equation of velocity. Now what we can do is that we know that dr cap by dt, right? So dr cap by dt, we know that, right? So dr cap by dt is just theta cap into d theta by dt, right? So we can substitute for that value. Now what we get is velocity vector is equal to dr by dt in the r cap direction plus r times uh, dr by dt is just d theta by dt in the theta cap direction, right? So that's r dt d theta by dt in the theta cap direction. So that's what velocity is for non-circular motions, right? Okay, let's use this. This is the equation of velocity for non-circular motion. So it has two components. If you look closely, it has a tangential component, which is theta cap, and then there is a radial component r cap. So a thing that is moving in a non-circular path, it could be elliptical, it could be anything. In that path, it will have an r cap component which is radially outwards, and then there will be a tangential component which is theta cap, okay, tangent to the path, okay, trajectory, and also r cap in this direction or into the inside if it is negative. So that's how a velocity will look like for a non-circular path. Now what we can do with this is that we can find out the acceleration for a non-circular path, right? So that's the next thing that we will normally do. When we found out velocity, let's find out acceleration. So acceleration vector is equal to dv by dt, right? So now what we have to do is just, we know v, now we need to take the derivative of v again, right? That's what we need. So it's d by dt of v is just dr vector r by dt in the r cap direction plus vector r, which is a function of time. This is a cap and this is a vector arrow, times d theta by dt, right, in the theta cap direction. So that's what we need to do. This is the velocity. Okay, I just substituted this equation into here, right? So that's the whole thing I did. Now I have to find out the derivative with respect to time of velocity. So that's what I'm going to do. So in the first part, you can see there are two functions, right? There are two functions in the first part, and there are three functions of time in the second part, right? R d theta by dt is also a function of time, and theta cap is also a function of time. So let's do the chain rule. Okay, you have to be careful when you do this because you could make mistakes easily with this. So in the first part you have two functions, so that's easier. So that's first function dr by dt, which is a vector, times d of r cap by dt, right? So I'm going to represent vectors just as r, and I will write down, you for unit vectors I'll write down r cap, so it's easier to understand with the notations. Okay, let's not complicate ourselves. So plus the second, again product rule. So the second is again dr by dt, right? So it's dr by dt so it's d square r by dt square times r cap. So that's the first part completed, right? So that's the first part. Okay, I just completed. Plus the second part, we have three vectors, right? So this is going to get a little bit messy, so look closely. So in the second part you will have r, which is the first function. So I'm going to take d r by dt, which is a vector, then I am going to write down the rest just as it is. Okay, plus now I am going to do the second function, d theta by dt. So it's r vector r times d square theta by dt square theta cap, plus the third I'll write down r vector r times d theta by dt times d theta cap by dt, right? So I just did a product rule just for that, so I got it just like that. Okay, now what I'm going to do is that I'm going to, there are some peculiar things inside this equation. Okay, something that we already know, right? So those two things actually are d theta by dt, which we know, and then the other thing is d theta cap d r cap by dt, right? D theta cap by dt and d r cap by dt, which we know. So we know from this equation 2, d theta by dt and d r cap by dt, right? So I'm going to substitute those values in here. I'm going to substitute those values, and you get what you get is dr by dt. This is lengthy, so be patient. This is not that complicated, it's just some differentiation. So I'm going to substitute for d theta dr cap by dt, so that's just theta cap times d theta by dt, right? So the rest of these things I'm going to write it again because I don't want to confuse you. I'll write it everything is the same, right? Dr square by dt square in the r cap direction plus dr by dt, right, in d theta by dt in the theta cap direction plus r times this value r times d square theta by dt square in the theta cap direction plus, okay, plus r times d theta by dt, and now I need to substitute for those value as well. So for that, d theta cap by dt is just minus r cap times d theta by dt, right? So I just substituted from equation 2. So that's the whole thing I did. Everything else is the same. Now what I need to do is just simplify this, right? We need to make this neat, right? The acceleration vector has to be smaller. Now what I can do is that I have to rearrange them. Now I'll rearrange them in terms of two things, right? First thing is just in terms of theta cap, right? So if you want, you must write this equation. Pause this video, write down this equation, and now look at this when it is rearranged, right? I'm going to rearrange them. So in the theta cap axis, I have dr by dt, d theta by dt, and then again I'll have, that's the first one, right, dr by dt in the theta cap direction, dr by dt and d theta by dt. Now in the theta cap direction there is dr by dt and d theta by dt again, and then in theta cap direction r times d square theta by dt square. Okay, so I'm going to write it down, okay, with some clarity. So again dr by dt times d theta by dt, 2 times that, plus r times d square theta by dt square. Okay, so that's what I have in the theta cap axis. Now in the r cap axis, so in the r cap axis I have d square r by dt square, and then I have r times d theta by dt the whole square, two of them. So r times d theta by dt the whole square with a minus sign, right? So I'm going to write that down, okay, here, just like that. Along with this whole thing, it will be d square r by dt square minus r times d theta by dt, the whole square, right? So it's a whole square. So that's what you get, right? Okay, d theta by dt, the whole square. So that's the whole thing. Now what I can do is just that this is called the acceleration. So it's acceleration vector a of t, right? This is the acceleration vector a of t, right? So let's put it in a box and call this equation uh, 4, I think, right? 4. Okay, now we got the acceleration vector. Now let's do what? Let's do something. Let's write down the component. So acceleration vector, remember velocity vector had two components in the theta cap and the r cap. Also acceleration now has theta cap and r cap components, right? So I'm going to write down them as simple as possible. A in the r cap direction is just d square r by dt square minus r times d theta by dt the whole square. That's in the r component. And in the theta component I have 2 times dr by dt, two of them, right? So two of them here, two of them are there, 2 times d, okay, times d theta by dt, 2 d theta by dt are there, plus r d square theta by dt square. Let's call this equation 5 for 5. Oh yes, and let's call this equation 6. Okay, this is the radial component of velocity acceleration, and this is the angular tangential component of velocity acceleration. So what can you get out of this now? Before 107.5 this lecture, we were always dealing with velocity vectors, right? So we only had the tangential component of velocity beforehand, right? We never considered about the radial component. Velocity had no radial component because you are constrained to move in a fixed radius. Now things have changed crucially, and now equations has become a bit more complicated because we have to manage for changing radius, elliptical or any kind of radius. We have to look at changing radiuses. Now this is the case. Now we can see that in normal cases, right? In normal cases, if you look at a normal problem, you will see that the angle, if theta angle is swept for some arc length s, then we have done before, we have approximated that s will be approximately equal to r times theta. We did this earlier, right? Remember that. So this approximation I did angular, small angle approximation and linear approximation in the earlier lectures, and from that you can say s equal to r theta. So ds by dt, which is the velocity, will be equal to r times, approximately equal to r times d theta by dt, and the acceleration will be r times d square theta by dt square, right? So that's normal case. Now if you look into this equation, there is, here it is r d square theta by dt square. Now there is r d square theta by dt square here, right? That's a normal component of acceleration. Apart from that, there is an additional component. You can see clearly there is an additional component just there, right? So what does that component gives you? This component. What is this component? This component is called Coriolis acceleration, right? Coriolis acceleration. We will learn that the force, Coriolis force, in the later part of the course. Acceleration, don't mind about the spelling, I'm sorry about that. So this is the Coriolis acceleration. So this is an additional component which is adding on to this acceleration. So if a body is rotating like this, right, there is a normal acceleration, tangential acceleration, and then there is an additional acceleration which will force the body to move faster. So it will add, so it is proportional to d theta by dt and dr by dt. The, if r is also changing, it is interdependent on r, change in r and change in theta, right? So it's a cross correlation term, right? with r and theta changes. R dot and theta dot is in there, right? So that's Coriolis acceleration. Okay, remember that this is the Coriolis acceleration. Whenever you are asked to do a problem where there is complicated trajectory which is not circular, then there will always be some additional acceleration. So you don't have to do all those solutions, right? You don't have to do complicated calculations, but all you have to do is write down this equation 6 and then find out the actual acceleration just right from there. Okay, straightforward from that you can find out the exact acceleration using this equation. Okay, this is a tool that you can use always. Now that's about Coriolis acceleration. That's the whole thing about acceleration. Now I'm going to finalize this chapter, right? This chapter of circular motion with a problem. It's going to be a little bit long problem. It's not that it is very simple, but it is going to take some time. Anyways, let's consider a case when there is a trajectory which is not exactly circle. Okay, some complicated trajectory. A particle is moving around, a body is moving around a planet, right? A planet in an orbit, right? In a complicated trajectory. It is not even elliptical, right? There is some additional kind of forces involved and it is complicated itself. Now what we can do is that, and the equation of that motion that where r is changing is b times theta, and it is given, and theta is also equal to c times t square, or let's simplify itself, b is equal to 2 theta. Okay, so it's easier for us to calculate. So c is equal to 3 3t square, right? So that's much more easier, and we have a number in the end, that's why. And let's call after, okay, this is the trajectory. We need to find out after t is equal to 4 seconds what will happen to the acceleration, right? So that's what we need to find out, what happens to the acceleration. And we also need to find out the trajectory of this path. So how does it this path looks like? Okay, that's the dilemma here, right? So how does this path looks like? That's the question. Straightforward. I hope it is clear. Very simple question, very straightforward. So from equation 5 and 6, I guess, yeah, 5 and 6, you can straight down write down the acceleration components in two directions, right? So acceleration, and you can find out the acceleration straightforward, right? So a theta was a in the theta cap direction is just, okay, let's before that let's do, okay, r is equal to b theta. So what will be d, uh, right, theta will is equal to, uh, let's call it ct square, right? So ct square, or let's call it by a basic name, right? Let's call it b theta before, right? So c is equal to b is equal to 2 and 3, c is equal to 3 is something I'm going to substitute later. Now let's find use this in a generic equation so that it has a basic form. So theta is equal to b times what, b times theta is equal to c t square, right? C t square. So d theta by dt will be equal to 2ct, and d square theta by dt square will be equal to 2c, right? So we got that. Now what we can do is that, now we can find out for, because it has terms d theta by dt in the equation of acceleration in the radial and in the theta cap direction, there are equations of d theta by dt and dr by dt. That's why I'm calculating this, right? Beforehand I need to calculate this. And now dr by dt, right? Dr by dt, well, r is equal to b theta, right? So it's b times ct square, right? So dr by dt is just going to be b times 2ct, right? So it's 2bct, right? So, okay, I got that as well. And d square r by dt square will be 2bc, right? 2bc. Okay, so we got them all right. Now let's substitute into the equations of a. So a theta will be d square r by dt square, right, minus r times d theta by dt the whole square. Okay, that was ar, right? Ar, sorry about that. I just confused it. Okay, so that's ar. So ar is that. So let's substitute those values. Let's substitute them, right? Straightforward. We got that d square r by dt square is 2bc minus r, which is what, r is equal to what, bec t square. So that's bec t square times d theta by dt the whole square, that is 2ct the whole square. So simplify that and you get what is 4 uh, 4. Okay, there is 2bc minus 4b c cube t raised to 4, right? Okay, so now substitute those values. So this is the equation of which is equal to ar, right? So let's put that in a box. Let's put that in a different color box so that we can identify that. Okay, so that's a that's a r. And now let's find out a theta, right? So it's a theta which is a tangential. We have discussed there is Coriolis in here. So Coriolis, as long as Coriolis is present, that is 2 times dr by dt times d theta by dt plus r times d square theta by dt square, right? So that's Coriolis plus normal. So well, as substitute that, so it's 2 dr by dt, right? So dr by dt is just 2bct. So it's 2 times, okay, d square by dt. I guess it's all right. Okay, it's right. Okay, so that is equal to 2 times dr by dt is going to be just what, 2bct times d theta by dt, right? D theta by dt is going, what was it, d theta by dt is 2ct, right? 2ct here. Okay, 2ct. So it's just 2ct plus r is just bct square, right? So r is bct square. I remember that. That's here. So it's bct square plus times 2ct square, right? So that's d theta by dt the whole square. So we got that all, right? We got that all simplified. Now let's simplify it further. So what you get is 8, right? So that's not bct square. Okay, so I have made a mistake. So this is not b to c, right? What was it? So it's d square theta by dt square was just, okay, oh, sorry about that. This is d square theta by dt square is just 2c, right? So that's a mistake I shouldn't have done. Okay, that's not cool. So it's just 2c times 2c. Okay, so we got all that. I think it's right. I think it's right. Yes, it is right. So what you get is 8b and c square and t square, yeah, plus b 2b c square t square. Okay, simple. So it's the same thing, bc square t square. So it's 10 b c square t square. So that is equal to a theta. I'm going to put that in a box as well, right? So I need it. Okay, that's something also I need. So I found out a theta and ar, right? Two vector components, a theta and ar. Now what I'm going to do is that I'm going to put down the values of a, b and c, right? So a, b, c and t, right? So for ar, I'm going to do it here. So ar will be equal to 2 bc minus 4 bc cube t raised to 4. That's 2 times b is just 2 times c is 3, right? C is 3. I hope I'm right. Yes, 3 minus 4b 4b is 2, right? Sorry about that. B is 2, okay, times 4b c cube t raised to 4. So c cube t raised to 4. C is just 3 cube, right? So it's 3 cube t raised to 4. T is just 4 seconds, so it's 4 raised to 4, right? 4 raised to 4, right? Okay, now I got that. Now what you can do is that you can take out the 2 times 2 times 2 3 outside, right? 2 times 2 times 3 outside. I did this before, so let me look at it. Okay, 2 times 2 times, okay, here it is, 2 times 2 times 3 and 1 minus 9 times 256. It's just numerical, so I hope you are capable enough to do this. So it's just 276 36, yes, radians per second. Okay, that's the value that you get. So it's a number and it is huge. Okay, what does this number tells us? Okay, that's the question. What does this number tells us? So we have found out AR. Let's find out A theta as well, right? So A theta was, right, A theta is just 10 bc square t square, right? Remember, okay, we did that. Okay, now that is 10 times b is 2 times c square is 3 square times 4 square is t square. Okay, so that is going to be equal to, I did this earlier, so it's 2880 radians per second, right? Oh, there is something I did this, but that's the problem. Okay, this is a positive value here. Okay, so this is a positive value, which is a huge number. Okay, that's only thing that we need to get. Okay, we are not going to calculate everything. We are just going to look at the trajectory, right? So we found out the value, and this is a huge number. A theta is a huge number with a positive number, right? Positive number, it's increasing. Acceleration is high, very high, right? So it's a big number, it's increasing from the start. Now AR, right? AR, when we did AR, I made a small error. That error is here. This number is big, right? So this number is very big, and this number is small, so this number is going to, this part is going to be small, so there is a minus sign here. Okay, I forgot about that. So what you can find out is that AR, again, AR is very small. Okay, very small, and it is decreasing. It's decreasing. I'm not saying that it is small. It is actually opposite direction. It's very big, but in the opposite direction. So it's decreasing. It's decreasing. It's a negative value, right? So that's the outage of that. Okay, so we have done the problem. Now there comes a point where we need to find out the trajectory, right? This is not the problem. Our problem is physics, right? So physically, what does this mean? So AR, okay, AR is proportional to minus of, right, something. So it was, if you look back at the basic equation, AR is proportional to what? So AR is proportional to the power of t raised to 4 here. Okay, and A theta was proportional to the power of t square. Okay, AR was minus t raised to 4 proportionality, and A theta had a proportionality which is, so AR is proportional to minus of t raised to 4. So it's decreasing, and A theta is proportional to, this is a minus sign here, plus of t square, right? So this is actually increasing. So what does this tells us? Okay, how is going to be the trajectory? How does it looks like? Okay, we need to find that out, right? So the a theta ar is going to be decreasing. That means when it is moving like this, right? So ar, which is the radial component is looking like this. This axis is the radial component from the center, right? So the radial component is actually decreasing. That means it's going to come inside. The particle is going to be moving towards the inside, right? And the theta component is increasing, right? So the tangential velocity is going to increase, so it's going to get faster. With time it's going to get faster, but towards the inside, okay, that's what it is. Okay, it's going to get faster, moving in the tangential direction, but it's going to move inside. So how does it looks like? Okay, how could it look like? So it start from here, let's assume that, and it's going to move around in this path, right, from a center point. Let's call it this center point, center. So it's going to move around and it's going to have to move faster, but it's going to have a smaller radius. So there is an enormous pull to this direction and enormous push to this direction. So it's going to move faster, but it's going to slowly reduce the radius, right? So slowly reduce the radius, and it's going to get smaller and smaller and smaller and smaller and smaller and smaller. It's going to start. So a path will look something like this, a spiral. Okay, so that's the path, and it's going to get faster as it gets to the center, right? When it reaches the center point, it's going to get faster, right? Faster. That's a spiral. Okay, this is a spiral motion. So what we have dealt with so far is an equation for a spiral motion. Okay, so we found that out. Now I could end it here, but I'm going to go a little bit further and do some more things. Okay, some numericals as well. Okay, I need to do something. I need to find out what is the time when radial acceleration is equal to 0. So remember, radial part AR had was equal to 2cb minus 4b c cube t raised to 4. We found that. So when will it be equal to 0? Okay, now all you need to do is just simplify this and you get 4b c cube t raised to 4, right? So when you simplify that, you get t is equal to c cube, and c will cancel, b and b cancel, and you get t will be equal to 1 by what, 2c square, right? 2c square the whole raised to 1 by 4. So this is the time when the radial acceleration, right? Radial acceleration is equal to 0, right? So when it this is approximately equal to 0 because it's so small, right? The value is so small. You can clearly see from this equation that it is going to be a fraction of c, right? It's a fraction of 1 in terms of c was we assumed c to be equal to uh, some value 3 or something like that. So it could be anything, but it's going to be small, right? So in the starting point of this trajectory, right, in the starting point of this trajectory, this path is going to have 0 radial acceleration. So it's not going to pull down without any force, right? It's not going to pull down at only the starting stage. After here it will pull down faster, right? As it approaches towards the center, spiraling in, it will start to pull down faster and faster. Okay, so this is something that you can directly see. And I want you to see one more thing, right? One more thing is when a theta, which is equal to 10b t square c square, right? So that is equal to 0. When will it be? It will be equal to 0. That means the tangential, this time is equal to, this will be 0 only when t is equal to 0 or t square equal to 0. So the only point where tangential acceleration, right, tangential acceleration is 0 is at the time equal to 0, right? When there is no velocity, no acceleration, so all the time it will have some kind of tangential motion. So tangential force, right, tangential force, I'm going to yellow, I'm using tangential force for that yellow. So the tangential force is always there, and it is going to increase, and it will spiral faster and faster and faster, and it is not going to get 0 never going to get 0, but the radial acceleration is going to get 0. There is a fixed value for that, and we found that out. Okay, we can do that from here. Okay, we did nothing more than simple calculation, right? Simple calculation, some arithmetics and some adjustment and some basic differentiation, and we got this. Now let's look at the one final case. Okay, one final case, and I'm going to close in. So the final case is when they are both equal, right? So b t square c square, which is the theta cap, right? So this is the tangential, which will be equal to 2bc minus bc cube t raised to 4 uh, times 4, I guess. Okay, times 4. Okay, so when this will be, which is a theta and a r is equal to 0, when will they both be equal to 0? So this might require a bit more arithmetics than we have imagined, so let's do this anyway. So you can rearrange this equation in a simpler way, and you can write 4b at 4bc cube t raised to 4 plus 10 dt square c square, right? So that will be minus 2bc will be equal to 0. I just rearranged that, and now what I can do is that I can simplify this, and I can divide this whole thing by 4b 4b cube, this thing. Okay, this thing I'm going to divide it with that. So you divide it with that, and you get something, this thing cancels, and plus 10 b t square, so you get 10 by b, and you get 10 by 4c, right? 4c t square, right? It cancels, minus 1 by 2c, I guess. Yes, c cube by, okay, 1 by 2c square, okay, is equal to 0. Okay, this is what you'll get. Now you have learned in from 8th standard, I guess. So ax square plus bx plus c is equal to 0 is a simple equation, quadratic equation. You can solve it by x equal to minus b plus or minus square root of b square minus 4ac by 2a, right? So you have seen this so many times. Let's use this here. So this is an equation of t raised to 4, right? T raised to 4. Now let's find out t square. So t square will be equal to minus b will be minus 10 by 4c plus or minus b square, which is 10 by 4c the whole square, right? Plus 4 by 2c square, right? 2c square, that's c. Okay, for a and c, right? For b square 4ac divided by 2 times a, that is 2, right? Okay, you got that. And it is very simple. So you get minus 5 by 4c plus or minus some square root of 100 by 16 c square plus 2 by c square times a half. There is a half here, so it's a 2. So that's what you get. Now you can simplify that. You can simplify that just as t square will be equal to minus 5 by 4c plus c square can be taken outside, so you get 1 by 2c, and square root of 100 by 16 plus 2, that's like around 9, I guess. It's around 9, so it's going to be 3. Square root of that will be around 3. Okay, approximately. Okay, I'm doing that anyway. So this is approximately equal to some minus 5 plus 6 by 2c, right? So that's approximately that. Okay, so this is approximately, it's not 3, it's going to be 2 point something 7 or something like that. It's going to be small. Okay, so it's not going to be 3, it's going to be approximately equal to 5. Okay, this is going to be approximately equal to 5. That means it's going to be small, it's going to be very small. So it's approximately equal to 0, so it's very small. That means, what does this mean, right? So what we have calculated is the point where a of r and a of theta are both equal, right? So where is it in the spiral? So in the spiral, where is this going to be equal to 0? So if you look at this equation, you can see that they are both equal at t equal to what, t square equal to approximately equal to some small number, right? T square equal to some small number, or t is equal to some approximately around the start. In the beginning stage, this thing have the same centripetal and the center towards the center tangential and radial acceleration. So it's tangential and radial accelerations are both equal when they are beginning, right? Only in the beginning stage. Afterwards it's not going to be the same. Afterwards this thing is going to get faster and faster, and the radial force will pull it down. Radial acceleration will pull it down, right? We haven't introduced force or anything like that, okay, up until now. I hope I'm clear. So up until now there is no existence of force for us, but the acceleration itself is managing this thing, and it can pull it inside, right, to the center. It can pull it to the center, and it will decrease and decrease and get to a halt or some. You can imagine that there is this, okay, let's do some more physics, okay, some basic thing. So if you think that this is a ball, this ball is going to rotate towards the center, what will happen? Right, the radius is decreasing but the tangential force is increasing. So if it's an actual ball, then the tangential force increasing, that means it's going to get into the center and it's going to start to rotate, right? It's not going to move in a spiral, but it's going to start to rotate when the radius, okay, the radius of the ball is bigger than the orbit orbit radius, right? If the radius of the ball get bigger than the orbit radius, that small, when it is spiraling into that smaller value, right, that smaller value where the radius of the ball is smaller than, bigger than the radius of the orbit, then it will start to rotate, right? It will just rotate, it will stay there and it will rotate. This is a very good thing that we see in universe, right? In the world we will see around many cases, we will see this thing, the same thing happening around everywhere. This kind of spiral motion, this kind of, you will see that in cosmology, in black hole mechanics, you will see this kind of motion. So this is the application of having the ability to solve this kind of problems, okay. And with that I'm going to close this. This is the longest I have done, and I hope you guys benefited from this. That's the only purpose for me here. I'm doing this whole thing for your benefit, and with that I'm going to close this lecture, and all the best luck for you guys, okay.